Our next presenter is the head of Realtime at OpenAI. Please join us in welcoming Justin Uberti to the stage.
All right. Welcome, everyone. It's so great to be here today. Really excited to be part of this first ever VapiCon, focused entirely on voice AI. There are a lot of people here. So many folks in the audience who are also interested in the same thing. One thing I just sort of mentioned, I think Jordan mentioned it earlier, was I first met Jordan about 2 years ago, and we were sort of eating burritos out in the street and talking about like where voice AI might go. And to see that like we're here now with our own conference, just kind of remarkable to see that. So I'm just really pumped to be here. When Jordan said, hey, would you like to be here at VapiCon? I was like, let's do it. So anyway, to the presentation. I was going to try to write a catchy title about like what was going on in the voice AI space and what we should all be excited about. But the main thing I felt was there are a number of questions I repeatedly get about like how should I be building my voice AI? What are the things I should be thinking about? And I thought maybe I should just talk about that. So with that, we'll get into the 3 questions that I hear the most. But first, I've been excited about the possibilities of voice for a while. I've been at OpenAI for the past year, and I lead the team that develops our real-time infrastructure, which powers ChatGPT Voice and the Realtime API. And before it, I was at OpenAI. I co-founded a startup that builds speech LLMs. And I also worked for 15 years at Google, where I led the creation of the WebRTC standard, the audio-video technology that's used by Google Meet, Microsoft Teams, and now a host of voice AI applications. And I think there's something about voice AI that speaks to something really fundamental. We've been using our voices to communicate with each other for the past 100,000 years. And this unique property has allowed humans to disseminate knowledge worldwide. And so even with the advent of written language, voice is still incredibly important in the AI age. And here's why. First, speech is the fastest way for humans to express their ideas. Over 4 times as fast as typing, especially on a phone, and much more effortless. And second, voice carries information that text just can't. Our voices are immediately recognizable, and they carry this significant extra information. We call this paralinguistics, the tone, the intent, the voicing. And finally, every person has the hardware for voice interaction built in. We can just talk. And so making a voice AI device just requires like an inexpensive speaker and microphone. So I think we're going to see these embedded AI devices everywhere, just because it's so easy for us to interact with them. Now, it's still early days for voice, and there's still many, many problems to solve. But I just want to play a quick clip to set the stage of why we should all be excited.
Hello, I'm here.
Oh. Hi.
Hi.
So this movie is 12 years old. 12 years ago, this was absolute science fiction. And now, you all are making this commonplace. It's incredibly exciting. Oh. Anyway, so on to the 3 questions. First, what's a voice agent? This term agent has become so overloaded that it can really mean just about anything. So I want to try to put a stake in the ground to help us kind of understand what we mean when we say voice agent to each other. Now, this meme was kind of inspired by Simon Wilson who had a quest to define what does agent even mean in the terms of agentic AI. And his definition was, an LLM that can use tools in a loop. And that makes a lot of sense for, I think, kind of like a agentic, off-doing stuff agent, but it's not exactly something for a voice agent, which may or may not even use tools. So let's see if we can make our own definition. So first, let's think about what might be considered a voice agent. So I've got Jarvis from Iron Man, definitely seems like it checks the box. This guy, kind of obsequious, but still seems like something you interact like a voice agent. What about this? Yeah, right, okay. My people here. All right. So, let's see if we can break it down to figure out, what are the actual criteria. So, first, the obvious one. It needs to interact with voice. It's right there in the name. So, with that sort of set, now we can talk about the next thing. It needs to be multi-turn. It needs to be able to easily refer back to other parts of the conversation. If I ask for information about the sports team, like the Mariners, who are in the baseball playoffs, and then I follow up asking when do they play next, the pronoun resolution needs to be unambiguous. You can't be like, I don't know who you're talking about. So Alexa, Siri, these other sort of one-shot interactions, they typically struggle here. And so I think that the key thing is it needs to be multi-turn and it needs to be have this conversational context. And then critically, it needs to be able to handle open domain queries. That's the main thing that separates this from IVR systems and other sort of dialogue flows that we see today. Otherwise, it's really just 3 if statements in a trench coat. So it needs to be able to handle open domain, and so that typically implies that it's based on an LLM. Doesn't necessarily have to be, but it needs to be able to handle these open domain queries. And so these queries, roughly summarized, is can it hold a conversation like a human? So this last criterion is a little bit different. One of the things that we see when we see users interacting with voice agents is that it can be very challenging for a single voice agent to maintain its context over a protracted conversation. So one of the ways we deal with that is by allowing a voice agent to hand off to other voice agents, and they each get their own clean context to have their conversation, maybe inheriting a summary of what was discussed from the previous voice agent. And this is something that I think is very well understood. There's a parallel to humans right here, that you talk to someone and then they go talk to somebody else and they hand off some context. And so there's this existing primitive that people know, and then we have these voice agents handing off in a multi-agent architecture. It just kind of makes sense. But I do think it's important that we sort of say that if you're running tools or whatever, that's not independent context. It needs to basically, a voice agent needs to have its own context. Anyway, this is my sort of attempt at a definition of voice agent. Be interested to see if other people have other criteria or have issues with any of these. But moving along. So this is the second question I get asked the most. Should I be building my architecture on a chained approach or on speech-to-speech? And so I have my own thoughts on this, but just sort of I'll take a step back. When I first saw GPT-3, back in the summer of 2022, the absolute next thing I wanted to do was see if I could make a voice wrapper around it. Put a speech recognizer stage in front of it, put a text-to-speech engine behind it, and let's see if I could talk to it. And so here's what we had in the summer of 2022, if someone can do the honors of clicking on the button here.
I'm feeling kind of hungry.
You should try the new restaurant down the street.
What is that?
The restaurant's name is The New Restaurant.
So, intelligence of these models has come a long way, as has the quality of voice and everything, but the overall, The overall architecture is exactly the same as what I had back in the summer of 2022. You've got a speech recognizer that takes its output, passes it to an LLM, and then the LLM streams tokens to a text-to-speech that then plays out. And in reality, it's a little bit more complicated. We've got this piece called turn detection that makes things very, very interesting, and I'll talk a little bit more about that later. But on the other hand, we now have these speech-to-speech models. And rather than being an ensemble of 3 different models, this ASR, an LLM, and a TTS, it's a single model. It's got a speech encoder that kind of converts like the input voice to hidden states. Those flow through the network to the speech LLM that then does its internal processing, and then image speech tokens that are fed to a decoder that are then played out as the output speech. And here, there's no intermediate text form. Everything is moving in this high-dimensional space between the layers of the network. And so it's got a lot of advantages, but in fairness, there are also some trade-offs. So I'm going to walk through that right now. So one of the things that customers do enjoy is with the chained approach. If you bring your own ASR, your own TTS, your own LLM, you can use different vendors for different stages. You might say, oh, I like DeepGram for ASR. I want to use OpenAI for the LLM. I want to use 11 Labs for text-to-speech. And you might have your own pricing. You might have your own things that you negotiate with each of them. And so it gives some flexibility to the customer. Second, you have this legibility, where you see the text coming out of the ASR. You see the text going to the TTS. And if there's an issue where a name is misunderstood or mispronounced, you can see exactly where that came from, what stage introduced the error. Third, the process of taking a text LLM and then expanding the token space to include voice tokens and then training the regimen with voice data makes the LLM less good at pure text tasks. And so you find that it's a very small percentage drop, but the same speech LLM versus a text LLM at the same size will do slightly less well on some various benchmarks. And so that's a trade-off. And then finally, a lot of customers want to fine-tune their LLM for their business use case. And it's much easier to fine-tune a text LLM than it is to fine-tune a speech LLM, where you need to make sure that the fine-tuning, since fine-tuning always damages the LLM to some extent, doesn't damage the speech production. All right, now let's get to the speech-to-speech advantages. So first of all, it can be much, much faster. There's only a single forward pass, only a single API call, only a single set of latencies to consider, and there's no TTS look ahead. Typically, when you feed speech into a TTS, before the TTS can know how to voice those words, it needs to look ahead a little bit into the sentence to see, oh, this is the tone that the user or the speech is going for. With the speech-to-speech model, that's all sort of inherent in this high-dimensional space. Second, the LLM is trained over all these different languages, so it's inherently multilingual. You can even switch languages in mid-turn, and that's something that's much different than a typical ASR, which often needs to be hinted or told explicitly, here's the language to expect. The instruction following for the speech LLM can also, for the single prompt, it can govern, here's how you should emit your output, and also here's the type of speech you should use in your output. For customer service, it might say, you should be very deferential, you should be polite, you shouldn't use any slang, and all that influences not just the semantics, the text, but the actual voicing of that text. So it's very powerful, especially in this RL era, to control exactly what the output of the model is with a single prompt. And then lastly, back to paralinguistics. Because we have these high-dimensional inputs going from the speech encoder through the model and to the output, the LLM can natively understand tone, it can understand pronunciation, it can understand non-speech things, non-verbal, non-textual things like laughter, and that's something I'm going to show you in a second here. So it really has a much better way to be significantly more, I think, empathetic in terms of understanding exactly how you're interacting with it. So I'll show a little demonstration of this. If I can get this to play, if someone wants to hit the button once again. So I was thinking of building this live demo where I basically would have like an AI assistant that would tell it to go to the next slide and everything. But they said no live demos here, unfortunately.
Per 114 grams. How much should I add to make it evenly 500 grams of calories? Excuse me. Excuse me.
Bless you. All right, let's figure out the kind of cheese portion to get you right at that 500 calorie mark. Right now, with the pasta and the cheese combined, we have about over 114 grams. Solving for Rex is going to be 4.56 grams. So you'd only need about 4.5 grams of cottage cheese to add those last 4 calories. That's a tiny bit, but if you want to round it up, you can add about.
你会说中文吗？
会啊，我会说中文，咱们可以用中文聊一聊。你最近在学习什么呢？
哇 ，ChatGPT 你的中文真的太好了，你怎么中文这么好呢？
哎呀，过奖了，我就是多练习，多跟别人聊天，然后看一些中文的节目啊、电影啊什么的，慢慢就进步了。练习真的很重要。
Well, today I need to create a marketing plan for 2025. Can you help me with that?
Sure. We'll start by identifying your main goals for 2025. Are you aiming to increase brand awareness, launch new products or services, enter new markets, or something else? Knowing your goals will help us shape the strategy.
We're going to get along just fine.
So the text is, a walk through digital canvas. On each screen, an invisible painter mixes. Call it artificial, I call it a wild workshop.
Nice job. Here's some feedback. Sounds. TH was good. Work a bit on weather and thankful here. Just remember to round your lips on W and use your teeth for V. You had a nice
So you can see that some of these properties I just talked about, the multilinguality, the ability to understand more of the input that's not just the text, all come through in what the actual customer benefit is. And so there are a lot of reasons to like speech-to-speech. Here's one more. I'll help. I think you just need to go to the next slide here. Okay. So the bitter lesson. This is an amazing essay by Rich Sutton. It's 2 pages. Everyone here should read it. But the key thing to take away is that if you try to break things down the way that humans think about it, and in some ways this whole sort of, I want to convert from speech to text, have text then go through the LLM, and then text to speech on the outside, that can be a very human way of thinking about it. But Rich says, these mechanisms don't work. The best thing to do is train end to end and let the machine figure out the representations internally. And those are the things that have given us the best gains in the past, is getting rid of our preconceptions of how things are supposed to work and use compute to figure out the best strategy. Anyway, with that, on to the last part. How can I stop my voice agent from interrupting me?
Hey, can you set
Bread is set for 9 a.m. tomorrow.
No, I wasn't done. I need it
Got
for
it. Adding milk to your shopping list.
I didn't
Okay, listen. Set a reminder for Saturday, 8 a.m. Reminder created.
You have got to be kidding.
So that all is probably painfully accurate to a number of people here. So how do we end up here? So this turn detection component, we want to invoke the LLM. We need to wait till we have the full user input to invoke the LLM, because the LLM is it's like a fire and forget thing. It's not like a streaming thing. So we need to know when the user started and stopped speaking. But if you stop too early, you end up interrupting them. And if you wait too long, then it just seems like your whole system is sluggish and it's not good. So it's a very, very hard optimization problem. So the simplest algorithms, voice activity detectors, they use a preset amount of silence to make the decision that the user is done speaking. And typically, people use around 300 milliseconds, to say, oh, users have been silent for this long, I'm going to go fire off the LLM. But the problem is, in normal conversation, humans can pause for well over 300 milliseconds. And so you have this weird way of talking to LLM sometimes where you're like, as soon as you maybe pause, you're like, just to make sure the LLM doesn't cut you off. It's not good. So some newer algorithms, they also consider not just the silence, but the actual semantics, the actual speech content to figure out, was the sentence that I heard a complete sentence? And so if you're saying he's a student at Stanford, it won't cut you off at he's a because that's clearly not a complete sentence, but it can still be ambiguous because that he's a student is still a complete sentence. So we need something more, and it turns out humans are actually pretty good at this. Not perfect, but they're pretty good at knowing when someone is about to cede the floor for turn taking. And prosody is a big part of this. There's a very interesting book. It's called How We Talk. Very interesting if you're interested in this problem to go read it. But there's 3 prosodic cues that can be very indicative of that the human is handing off a turn. And the pitch contour change, if there's a question saying what do you think? That little uptick on that last syllable, is a very clear cue that you're about to finish your sentence and someone else should respond. There's a couple other things that are used across cultures and everything. But this set of features allows humans to have easy turn handoff, typically with only 200 milliseconds between turns. Much, much more accurate than just using semantics or just using silence. So I think we need these sort of next generation algorithms to be able to take advantage of these unique things. But it's just a really hard problem. Even if you solve things like prosody, you still have to deal with, oh, you heard some non-speech noise. I need to decide very, very quickly, was that actually speech, or was that just somebody kind of shuffling some papers in the background? Also, we see cases where the assistant, when it's speaking, that audio bounces off the walls, comes back into the microphone, and the assistant can actually even interrupt itself. And finally, almost all these use cases assume there's only a single person that's interacting with the assistant. As soon as you have the case where maybe you're in a meeting, you don't want the assistant going off and responding, oh, what can I help you with? Every single time somebody speaks. It'd be the worst assistant ever. So they're just some very, very challenging problems. In many ways, humans have to think very carefully about when they speak. What did I say recently? Do I have something interesting to say? What do people think about me? What's my status? All the sort of stuff that goes into should I speak or not. It's a hard problem. And so we end up in this situation where we have these turn detection models that are 100,000 parameters. They're controlling the operation of these incredible language models with 100 billion plus parameters. And so, we might say, what is our way to kind of move out of this regime? How can we get to a better outcome? Ultimately, I think that we need to have the core model able to really think about this and solve this problem. I think that if we train end-to-end, we show the model these examples of here's how human conversation works, and then we just let it do its thing. I think we'll come out to a much better set of solutions than trying to make pound turn detection into the right shape. Now, I think there's a pattern throughout all of AI that you don't always jump to the final solution right away. You don't always train end-to-end immediately. A lot of times you build the shape of the thing by combining pieces together, by ensembling things. And from that kind of gives you a little scaffolding to finally build the right thing, the right solution that allows you to get the true end-to-end behavior. So I think we're kind of still in that phase right now where we're still doing that scaffolding. But I'm really excited where things go next, because I think we are at the cusp of really getting to machines that you can interact with and feel like it's a real human on the other side. So I'm really excited about the possibility. I'm really excited to be here today. And I hope you all go out here just as excited as me to go build these next set of voice applications. Thank you.